Thank you to Odoo for sponsoring this video. And welcome to Aviation Republic, my name is Joe. Here's a question for you. If you were stopped in the street or suddenly awoken from a deep slumber and asked, what are some of the most significant aircraft ever built? Would this one make the list? Probably not, right? The Mustang, Spitfire, Lancaster, B-17 maybe. Even with faculties not dulled by sleep, we might throw out the Corsair, F4U, Grumman Tomcat, Hawker Fury, B-52 even. Solid choices for sure, but it still wouldn't be this one. The aircraft we're covering today is one of the most overlooked. A machine built by a company that made locomotives and refrigerators with zero modern aircraft design experience. But somehow they managed to cobble together a bomber that flew like a fighter, that set multiple world records and went on to serve in more air forces worldwide than I could shake a stick at. America loved her so much they built hundreds under license. She fought wars in almost every continent. Even to this day, she's still going, 75 years after her first flight, still flying for NASA. So grab your goggles, tea and biscuit tin, because this is the story of how a bunch of young engineers in a garage led by a brilliant but eccentric designer built the legendary English Electric Canberra. Now this is a big story, and I wouldn't be doing her any justice if I tried to cram everything into a 25-minute story. I decided to break this into 3 parts. Part 1, the one that you're watching now, is about the design and development story of the Canberra. In part 2 we'll cover all the remarkable variants that made her the Swiss Army knife of the jet age. And part 3, well, that's the American story. How the USAF fell in love with the British bomber and made it their own and turned it into something entirely new. Have you ever had that one idea you just can't shake? Like, this could actually be something. And then you realize you need a website. And suddenly you're thinking, oh no, not again. My first website back in 1998 was straight up HTML chaos. Then came Dreamweaver, then WordPress, and honestly, every one of them took way too long to get from idea to, okay, this looks decent. But if I were to build another website today, like say to finally launch my biscuit empire, I'd use Odoo's website app. And here's why. It's simply so much faster and easier to manage than anything I've used previously. You can create a whole site in just 4 steps with no coding needed. You pick your site type, industry and goals, choose your colors or upload your logo, add your pages and features, and pick a theme. That's it. The structure's done. Then it's all about customizing by dragging and dropping blocks. It's super intuitive and you can customize everything. Text, colors, animations, images, no coding, no stress. It's perfect for anyone who wants something that looks great without having to lose weekends and evenings watching endless how-tos and tutorials. But wait, there's more, the most splendid part. Odoo's first app is free for life, so you can create your site for free for life. With unlimited hosting, support, and even a free custom domain for a year. So if you've got that idea keeping you awake at night, go and make it real by clicking the link in the description and give Odoo's website app a try. Thank you to Odoo for sponsoring this video. Now back to the story. So where do we begin? Well, to really even begin to understand the legendary Canberra, it's important to step back and take a broader look at the state of aviation among the vanquished and the victors of the Second World War. Over in the Soviet Union, they were busy making up lost ground fast, catching up nearly a decade of technological progress in a single leap by copying the American B-29 as a Tu-4, and it wouldn't be long before they started fitting jet engines to their bombers. Over in America, they were experimenting with all manner of jet-propelled bombers, with the beautiful swept-wing Stratojet first flying in 1947. Of the vanquished, Germany had been picked clean, with most of its jet technology being carted away either to Russia or America, while Britain was left with the scraps. Bomber Command was still flying the piston engine Avro Lincoln, which was little more than a stretch Lancaster, impressive in 1945 but utterly obsolete by 1947 and a little old-fashioned, even more so when compared to the likes of the B-47, which looked like it was a Buck Rogers jet from outer space, and this disparity left many in the RAF and the population at large asking the same question. Where were our shiny futuristic swept-wing bombers with at least 10 jet engines? However, it was not for lack of trying. The Air Staff and Ministry of Procurement had first held a conference as far back as 1943 to ponder the question of jet-powered bombers. If any country could do it, then it was Britain. No other country even came close to possessing the abundance of incredibly talented aeronautical engineers and designers who could, while working under challenging conditions, design high-performance aircraft in damp and drafty wooden huts on nothing more than sheer will and tea. As the war rolled into 1944, the Air Ministry, with the assistance of one of the aforementioned talented engineers, W.E.W. Petter, helped draft specification B1/44 that laid out the beginnings for a bomber with an all-up weight of 32,000 pounds, a payload of 4,000 pounds, and be maneuverable at both high and low altitude. However, this specification came with one requirement that was particularly adventurous. The top speed for this aircraft was put down as 530 miles an hour, and to get there it would need to be powered by a pair of those newfangled turbojet engines, adventurous since the first jet to see RAF service was the Meteor in July 1944. In spirit, this bomber design was to be the successor of the de Havilland Mosquito, but gone were the days of bombers bristling with turrets and guns pointing in every direction. This new aircraft would be totally unarmed, relying entirely on speed and altitude to evade interception, something that piston engine aircraft simply couldn't do with the future skies looking like they'd be filled with jet fighters. However, there was an issue. At the time, the most powerful and reliable jet engine available was a relatively large and rotund Rolls-Royce Nene. This engine, with its large diameter, would present an aerodynamic challenge to most designers, but to William Teddy Petter, who at the time was chief designer at Westland, it was an opportunity to put his ideas into practice. For those of you who have seen my videos on the Fallen Gnat and English Electric Lightning will know that I'm somewhat of an admirer of Petter, to put it mildly, and rightly so, because he was a genius. He was, however, also a troubled man, and at times difficult to work with, ready to dismiss other people's views despite their best intentions. This attitude would sometimes lead to sabotaging his own efforts. One example of this hard-headedness would cost him the NATO lightweight fighter competition when his little gnat lost out to the Fiat G91 simply because he wouldn't make one simple modification. And it would be this hard-headedness that would almost break the Canberra project, but that's all in the future. Although the Ministry of Aircraft Production hadn't awarded Westland any specific contract to build B1/44, Petter nevertheless quickly got to work with his usual enthusiasm on initial sketches, even managing to convince Westland to put up some private venture capital to fund a mock-up. His first layout, from which I can gather, was called the P1056, which was to be pushed along by a pair of Metropolitan Vickers turbojet axial flow engines that sat inside the fuselage. These engines were to be fed by a split-nose air duct passing under the pilot, giving it the rather unfortunate appearance of a pig, a flying pig no less. Naturally, this engine layout created all manner of issues with finding space for a bomb bay, which ideally would be best placed near the centre of gravity. The same concern went for the fuel, which too had to be located in such a way to avoid balance problems. Of course, this layout simply wouldn't work, so he started to think about relocating the engines to other parts of the airframe. For instance, they could be placed in the wing roots, as seemed to be the fashion of the day, or alternatively in the cells along the wing, the beginnings of things to come. As I mentioned earlier, Teddy Petter wasn't just a brilliant designer, he was also an unusual and often difficult man. Throughout his career, he had the habit of suddenly vanishing from work for weeks at a time, usually when pressure or frustration mounted. Nobody ever quite knew where he went, although it was said that he would retreat to a monastery or religious commune, immersing himself in his deep Christian faith. Then, just as suddenly, he would reappear without notice, refreshed, energized, and brimming with new ideas. These mysterious disappearances only added to his reputation as a man of both genius and eccentricity. In April 1944, at the height of his work on a twin-engine bomber, Petter slipped away once again. And it couldn't have come at a worse time. During his absence, Westland had begun work on a new naval specification N1144, and all progress on Petter's bomber ground to a halt. When he finally returned, he found that Westland had moved on without him. Knowing that the company was short on resources, unable to pursue both the naval fighter and his own project, and feeling that management had conspired against him, he resigned on the spot. But before walking out, he somehow managed to secure the rights to his bomber design, a decision that would prove decisive, because it was this very concept that he would soon carry to English Electric, where he would design and build a Canberra and then one day breathe life into the Lightning. In the late 1930s, the English Electric Company wasn't building aircraft. In fact, it hadn't built one since 1923. The last was the Wren motor glider, a rather sad little machine of which only 3 were ever sold. By 1926, English Electric had quietly abandoned aviation altogether and returned to what it did best: heavy locomotives, turbines, and big industrial engineering projects, proper North Country fare. But the world was changing, and fast. After the Munich crisis, the British government pushed industry to rearm, enlisting major manufacturers under the new Shadow Factory scheme, a program that built government-funded plants, often alongside existing works, to rapidly expand aircraft and engine production in preparation for war. English Electric joined the effort, drawing on its skilled workforce and its established Strand Road works in Preston, which became the management and engineering centre for the company's new aircraft business. At the same time, a vast new factory and airfield were built at Samlesbury, located between Preston and Blackburn, and this was no modest effort. By 1939, Samlesbury had 3 wide runways, extensive hardstands, taxiways, enormous hangars, and 750,000 square feet of floor space. It was the largest purpose-built aircraft assembly and test site in Britain. By the outbreak of the Second World War, English Electric was deep in licensed production of the Handley Page Hampton bomber, eventually completing around 700 airframes. Later on came the 4-engine Halifax, of which they built more than 2,100, more than Handley Page themselves. At the wartime peak, they were producing around 60 heavy bombers a month. This transformation wasn't easy. The company's formidable and greatly respected general manager Arthur Sheffield, who'd built his career in locomotives, described building aircraft as working with bent tin and alloy. By 1945, Sir George Nelson, English Electric's chairman, could see that the rapid pace of wartime aircraft development wasn't about to slow down. Powerful new jet engines were transforming both military and civil aviation, and the companies that mastered them would define the future. Sir Nelson also recognized that not every wartime aircraft had been a success. Some designs were flawed, some factories had struggled, and reputations had been made or broken overnight. That left an opening for a company with strong engineering foundations and fresh ambition to step into the arena and join the ranks of true aircraft manufacturers. No doubt Sir Nelson also had plenty of friends in the right places who would see to it that English Electric were not left by the wayside once the shooting had stopped. It may also have helped that certain voices in government were urging the decentralisation of industry away from the south of England. But whatever the motivations and reasons, Sir Nelson knew one thing above all: if English Electric were to have a seat at the top table as an aircraft manufacturer, and not just a builder of other people's designs, he would need extraordinary talent. However, there was one glaring issue. English Electric hadn't had an aircraft design office since 1923. They could build whatever other firms designed, and brilliantly. In fact, When the shooting did finally stop, English Electric were assigned a new job, licensed building the de Havilland Vampire, which they built nearly 1,400 of these aircraft in 4 years. But designing their own from scratch, that was a different world. So Nelson knew he needed the right man to lead a new design team. His choice was Inspired, William Teddy Petter. Although it must be said that he was introduced to Petter via the Old Boy Network as the inspired choice. With a nod of approval from the Ministry of Supply, Petter arrived in Preston in July 1944 as Chief Engineer of the Aircraft Division, carrying with him the blueprints for a jet-powered successor to the Mosquito fighter bomber, for what he believed was a once-in-a-lifetime opportunity to build an entirely new design team within one of Britain's most powerful engineering companies. As chief engineer, not just chief designer, Petter naturally expected control over the experimental workshop at Strand Road. He believed that prototype and experimental work should be completely separate from the production line, which was bound by strict rules and quality control routines designed for mass manufacturing. It was an outlook that would soon test his relationship with Arthur Sheffield. While those tensions would brew, Petter turned his attention to building the design team, setting up shop in a very unlikely place, a former motor showroom and garage on Corporation Street near Preston railway station. It has to be said that conditions at Corporation Street were, even for the time, quite primitive, but new recruits being shown around the place were promised that this was only a temporary home and that they would be moving soon, though in the end most of them would spend the next 3 years working there. But Petter wasn't interested in comfort when he began assembling his team. He wanted young, ambitious engineers willing to take risks. He wanted sharp minds with something to prove. Among Petter's smartest moves was recruiting Frederick Page, a gifted aerodynamicist from Hawker. Page had just developed spring tab controls for the Hawker Tempest, a system that allowed the fighter to stay controllable at speeds beyond 400 miles an hour, crucial while chasing down V-1 flying bombs, and was just 27 years old when he joined English Electric. To give you an idea how highly regarded he was, when he handed in his notice at Hawker, Sidney Cam had apparently advised him that, "You must be mad to leave Hawker, nothing happens north of the Thames." Mad or not, by early 1946, the design department would grow to over 200 engineers. Names like Di Ellis from Vickers as chief aerodynamicist, along with Ray Creasy, joined the group of men who would go on to shape not just the Canberra, but also the Lightning, the TSR-2, Jaguar and Tornado. Petter's genius was not just for having an eye for engineering, but also for talent, managing to build what one historian later called the preeminent aircraft development team in Europe. And it all began in that shabby garage in Preston. Now Petter firmly on board, English Electric was added to a short list of companies, alongside such venerable outfits as Vickers, Avro, Short Brothers and Handley Page, tasked with studying new specifications for Britain's first generation of jet-powered bombers. Those firms immediately set their eyes on the large 4-engine strategic machines, aircraft that would ultimately evolve into the Vickers Valiant, Avro Vulcan, Short Sperrin and Handley Page Victor. That left English Electric with a unique opportunity. While the others pursued heavy bombers, Petter and his team turned their attention to the smaller, faster, more agile twin-engine medium bomber developed under specification B3/45, a requirement that conveniently Petter had helped to draft and was closely related to the earlier wartime proposal B1/44 that he'd been working on at Westlands before his abrupt departure. The goals for this new specification were just as ambitious as the previous one. This new aircraft would have a service ceiling of 50,000 feet, a cruising speed exceeding 500 miles an hour, a range of 1,400 nautical miles, whilst hauling a 6,000 pound payload. And like specification B1/44, it was to have a crew of 2 and equipped with an advanced radar system based on the H2S design, to allow blind bombing through clouds or at night. This last requirement was considered super critical, to the point that the whole concept was pretty much based around the idea of being able to carry out blind bombing. And unlike the Mosquito before it, This new bomber would carry no defensive armament whatsoever, instead rely entirely on speed and altitude to stay alive and out of trouble. For a time, Petter and Freddie Page looked at all manner of configurations for the new aircraft. The initial designs, the ones that Petter had brought over from Westland, had a layout of 1 or 2 engines in the fuselage or in the wing roots. The issue was that at the time, as mentioned earlier, the most powerful and reliable jet available was the Rolls-Royce Nene. This large centrifugal flow engine produced about 5,000 pounds of thrust. However, there were plans to produce a turbojet more than twice as big as the Nene, running with a sea level thrust of 13,000 pounds. At first, Petter was captivated by the idea of housing a single powerful jet engine inside the fuselage, a perfectly clean circular design with minimal drag. It was elegant, simple, and promised superb aerodynamics. But it didn't take long for reality to intervene. The engine's diameter was enormous, and once it was placed in the center of the fuselage, there was simply nowhere, at least anywhere near the center of gravity, to put the bomb bay. Reluctantly, Petter had to abandon the concept. Looking for alternatives, he turned to Rolls-Royce to see what other engines were on the horizon. So, in May 1945, together with Frederick Page, Petter travelled to the Rolls-Royce factory at Barnoldswick to pay a visit to Stanley Hooker, the company's brilliant chief engineer, to discuss a promising new development, the AJ65 axial flow turbojet. It was possible that this engine would be the answer. It had a narrow diameter, it was more fuel efficient than the bulky centrifugal flow designs like the Nene, and best of all, it also promised to put out around 6,500 pounds of thrust, a considerable amount in those early days. For Petter's new bomber, this engine was the perfect fit, literally. But there was a catch. The AJ65 was still highly experimental. The early prototypes, as it was explained to them, were experiencing aerodynamic surges, compressor stalls that led to vibrations which, on occasion, caused blades to snap off. But they shouldn't worry, as they were confident that these problems would all be solved soon. As a point of interest, according to Stanley Hooker's excellent book, Not Much of an Engineer, it took about 7 years before the AJ65 could get a clean bill of health. 7 years, when Rolls-Royce had made the Nene work in as many months. However, their reassurance was enough for the general layout of the aircraft to be settled. Now, instead of burying the engines in the wing roots, which would have required bulky fairings that cut deep into the wing structure, they instead moved the engine with its smaller diameter outboard in tubular nacelles, leaving the fuselage clear for payload, equipment and fuel tanks. This layout also provided a safety net. If the AJ65 wasn't ready in time, they could house the larger Rolls-Royce Nene engines in modified nacelles without having to affect the entire airframe. It seemed that everything was going super swimmingly so far. I want to take a second here to thank you so much for watching. I'm truly grateful to share my love of aviation with fellow enthusiasts like you. So if you're enjoying this story, please take a quick second to hit the like button. It's a small gesture that makes a huge difference in helping me reach more aviation fans. Now let's get back to the story. Now that the engines were to be mounted in the wings, there was the important question of the wing itself. What kind of wing would the aircraft have? Would they be straight or swept? How thick would they be? All very important questions. At that moment in aviation history, everyone was obsessed with one thing: speed. Designers around the world were pushing their aircraft closer to the speed of sound, and to get there, they turned to a new idea: swept wings. Angling the wings backwards helped delay a dangerous aerodynamic effect called compressibility, the point where airflow over parts of the wing begins to approach the speed of sound. As that happens, shock waves form, drag spikes dramatically, control surfaces stiffen up, and the aircraft can suddenly lose lift or even stability. It was the invisible wall that early jets kept slamming into as they approached Mach 1. The swept wing was the fashionable solution, and it worked well for big, powerful aircraft like the American Boeing B-47, which had long, thin, highly swept wings designed to cruise fast and high. But Petter wasn't designing a heavy intercontinental bomber. He was building an aircraft that had to climb quickly, turn tightly, and operate in any weather. And crucially, he needed it now, and so did Bomber Command. But the need for such an aircraft went far beyond keeping pace with technology, the Americans, or even the Soviets. Britain still had vast global commitments, treaties, alliances, and responsibilities stretching from Europe to the Middle East and far beyond what became known as East of Suez. The RAF wasn't just preparing for the next war, it was already stretched thin, policing the remnants of its once vast empire and supporting new defence pacts in a rapidly changing world. In the Middle East, Britain was bound by the Baghdad Pact, maintaining air power in places like Cyprus, Aden, and the British naval base in Garn in the Indian Ocean. Imagine being based in Garn. The RAF needed an aircraft that could reach these distant outposts quickly and carry out reconnaissance or strike missions at a moment's notice. So this wasn't about building the biggest bomber in the world, it was about building the right one for the kind of conflicts that Britain was actually facing. There simply wasn't time to experiment with large swept wings whose behaviour, especially at lower speeds and in turns, was still poorly understood. The aerodynamics of large swept wings, particularly their lateral stability in turns, remains something of a mystery. Building a strong, stiff swept wing of that size would also have been a structural nightmare, heavier, more complex, and far more time-consuming to develop. Wing design was something Petter had vast experience with, having learned hard lessons from the Western Welkin, a high-altitude fighter he designed during the war. The Welkin's wings were incredibly thick, which gave the aircraft great lift in thin air, but proved disastrous as it neared the speed of sound. At around Mach 0.6, the air over those fat wings began to form shockwaves, causing a violent rise in drag and a sudden loss of control, classic compressibility. Petter saw firsthand how a design built for altitude could be crippled by speed, and he carried that lesson with him. When it came time to shape the Canberra's wings, he knew exactly how thin and clean they needed to be. Although he did consider wing sweep, he understood from his earliest calculations the specification could be met with engines producing 13,000 pounds total thrust. He said of this, "And with this level of thrust, sweeping back the wings and tail would have been pointless and would only have added weight, and the sweep was hardly worth it, increasing the critical Mach number from only 0.8 to 0.9. Instead, he went for an essentially straight wing, which one British admiral is quoted as saying when first seeing the aircraft, "The Canberra suffered from having been designed in the era between knowing how to make propeller planes look very cool and knowing how to make jets look very cool. This intercool period resulted in the aircraft looking like a child's error. Please let's all come together to forgive the dear Admiral." However, I'd like to point out that this wing is not quite as simple as it first appears. Between the fuselage and the engine nacelles, the wing had a constant width, a huge 19-foot chord. That's the distance between the leading edge and the trailing edge. Think of it as nearly 20 feet of wing stretching back from the front to rear. That enormous depth gave him room to build strength into the structure and house the landing gear, all while keeping the wing relatively thin as a percentage of its width. Outboard of the engines, the Canberra's wing tapered, becoming narrower towards the tips. Although it appeared almost straight, the wing actually had a slight sweep, about 4 degrees on the leading edge, while the trailing edge was swept forward by about 14 degrees. Measured at the quarter chord line, which aerodynamicists use as the reference for wing sweep, the Canberra's wing had a sweep back of just under 14 degrees. Enough to give it a hint of modernity, but nowhere as near as dramatic as the angles of the B-47. For the aerofoil shapes themselves, Petter chose two profiles, a thicker inboard section with a slight camber and a thinner uncambered outboard section. Now, what does cambered and uncambered means? Think of most aircraft wings. They have a distinct hump on top like a gentle hill. That curve is called camber, and it's brilliant at generating lift at low speeds, but at high speeds and high altitudes, that same curve creates extra drag, which the aircraft will waste energy trying to overcome. An uncambered wing is different. Its upper and lower surfaces are nearly symmetrical, almost like a teardrop lying flat. Although it sacrifices some lift at takeoff, once you're up high where the air is thin, it's far more efficient. The Canberra's wing was what you'd call low aspect ratio, specifically about 4.3 to 1, meaning it was short and broad, more like a falcon's wing. This design traded some aerodynamic efficiency for structural strength and agility. Now that might sound like a disadvantage, and normally it would be, because stubby wings create more induced drag, especially in turns due to stronger wingtip vortices. But Petter was playing a longer game. A low aspect ratio wing made the structure inherently strong and light. Unusually, the wing structure didn't pass straight through the fuselage the way it did on most aircraft. Instead, both the main spar and the rear spar bolted directly to substantial forged frames, solid pieces of machined metal, leaving the interior space completely free and unobstructed. It was cleaner, simpler, and gave more room for fuel tanks and equipment. The low aspect ratio also held a nice advantage: exceptional roll response. Let me explain. When an aircraft rolls, two forces resist it. The first is aerodynamic dampening. It's like trying to wave your arm underwater. The air itself fights the motion. The longer your wings or the longer your arms, the more air or water they have to push through when rolling, and the more they resist. The second is rotational inertia. The wing's physical resistance to twisting because of its mass spread far from the center. It's like trying to spin a long pole versus a short stick. Long wings have lots of mass out at the tips, far from the axis of rotation, and they don't want to start or stop rolling. The Canberra's short compact wing had both low aerodynamic dampening and low rotational inertia, less air to push through, less mass out at the extremes. It could snap into a bank almost instantly, faster in fact, than most fighters that might try to intercept it at altitude. For a bomber, that kind of agility was unheard of. If a fighter got on your tail, you could jink and roll unpredictably, making yourself a nearly impossible target. Canberra crews in the Suez Crisis and early Cold War noted it could outmaneuver interceptors at altitude with small, sharp rolls. And because the wing was so stable and controllable across a wide range of speeds, the Canberra proved just as effective at low altitude later in its career as it had been at high altitude in its early days. But here's where Petter faced a serious engineering challenge. The jet engine sat right in the wing, and their exhaust pipes had to pass straight through that main spar. So how do you maintain structural strength when you're punching a hole straight through your primary load-bearing member? His solution was elegant. Instead of building up the spar from multiple pieces, he used a light alloy banjo forging. This was a single piece of metal machined and drilled to carry the spar loads smoothly around the jet pipe. It was simple, strong, and typically Petter, solving a complex problem with a clever piece of metalwork. There was also a rear spar running along the wing to take the loads from the flaps and the ailerons. Unlike the main spar, which ran straight across, this one followed a more winding route out to the wingtips, accommodating all the control surfaces. The rest of the wing was surprisingly delicate, using thin gauge light alloy which helped keep the weight down. The leading edge was formed from a single sheet of aluminium wrapped smoothly around from the front to about 40% of the way back along the cord and bonded to internal stiffeners using Redux adhesive. This created a beautifully smooth, accurate profile, critical for avoiding turbulence and maintaining a clean airflow at high speed. In fact, Petter was so obsessed with getting this profile perfect that the whole wing was jig built, assembled in precision fixtures to guarantee accuracy. For sure, this was no experimental workshop cobbling together a prototype. Their very first aircraft used pre-production jigs designed to build 20 or more Canberras. This way, every wing that came off the line would be identical. Interestingly, the ribs weren't even attached directly to the wing surface. They passed underneath the stiffeners that were held in place by miniature eye bolts and threaded anchor cleats. tiny screw adjusters that allowed the team to tune the wing profile against external contour boards until it was perfect. The goal was to maintain laminar flow over the wing surface, smooth, undisturbed airflow that slips over the wing like water over glass, rather than tumble it into turbulent eddies that create drag. Get the profile accurate enough and the boundary layer, that thin film of air right against the skin, stays laminar all the way back to the main spar. No bumps, no joints, no protuberances to trip the flow into turbulence. Now, Petter wasn't entirely sure this would work in practice. Wind tunnels of the day weren't large enough or powerful enough to simulate airflow on a full-sized aircraft at high speed, and the ones that the Germans had built had all been pinched by our allies. Plus, in service, the wing would get scratched, covered in dirt and dead insects. But he built it right anyway, because if it looked right, it probably was right. Better still, Petter designed it to operate at a low angle of incidence. In other words, it didn't need much tilt to generate lift. Imagine holding your hand out of a car window. If you angle it steeply upward, you feel massive resistance. That's high incidence. Lots of lift, but also lots of drag. Now, if you hold it nearly flat, just a gentle slope, it glides smoothly through the air. That's what Petter achieved. By keeping the wing at a low angle, the airflow stayed smooth and efficient even at 40,000 feet, where most aircraft were gasping for performance. And here's where it all came together. The key to all of this was wing loading, which means the amount of weight the wing carries per square foot of surface. The Canberra's was just 48 pounds per square foot, much lower than any contemporary bomber. To put that into perspective, it meant the wing had plenty of area to support the aircraft's weight without working too hard. Low wing loading gives an aircraft superb agility. It can turn tighter and respond faster. It also meant that a Canberra could fly at slower speeds without stalling, take off and land on short runways, and climb rapidly to altitude. But Petter had another trick up his sleeve: thrust to weight ratio. This is a measure of how much engine power you have relative to the aircraft's weight. Most bombers of the era had a ratio of around 0.25. The Boeing B-47 had a thrust to weight ratio of around 0.22, enough to get the job done, but nothing spectacular. The Canberra's, on the other hand, was between 0.32 and 0.37. Now, that might not sound like much of a difference, but it meant that the aircraft had muscle to spare. Combine the Canberra's low wing loading of 48 pounds per square foot and the generous thrust-to-weight ratio gave it fighter-like agility, which allowed it to climb rapidly and turn tight enough to frustrate most fighters of the day. The result was pretty impressive. The B-2, the first full production Canberra, could reach 570 miles an hour at high altitude with a service ceiling of around 48,000 feet, all without the wings ever entering true supersonic flow. It achieved this not by brute force, but by being aerodynamically clean. Because the wing operated at such a low angle, the airflow over the uncambered surface stayed smooth and subsonic, even when the aircraft itself was flying at nearly 90% the speed of sound. And there were other hidden advantages. The wing's simple, gently curved shape meant no complex fairings or fillets, or if you're French, filets, were needed to smooth the airflow where it met the fuselage and engine nacelles. This reduced drag, made construction far simpler, because there were fewer parts to build, fewer things could go wrong. The wings may have looked simple, but they were a work of engineering art. The controls were also refreshingly straightforward. Unlike many aircraft that used complex cable systems where pulling the stick tugs on wires running through pulleys all the way to the tail, the Canberra instead used solid push rods. These are direct mechanical linkages, rigid tubes that transmit movement instantly from the cockpit to the control surfaces. Simpler, more reliable, lighter, and crucially, they gave the pilot precise, immediate feedback about what the aircraft was doing, meaning they could feel the air loads through the control column. Although the B-2 model and similar early variants lacked power-boosted controls. And for the pilot, the lack of these power-boosted controls and an autopilot meant that handling could be a bit tiresome during long flights. despite the aircraft generally being pleasant to fly. But getting the controls to feel right, not too heavy, not too light, required very precise aerodynamic balancing. There were three main techniques available to achieve the right balance. These were horn balances that stick out ahead of the hinge line, internal shrouded balances that are hidden inside the control surface, and various types of tabs. These are small auxiliary surfaces that move to help push the main control surface. Think of trim tabs. For the Canberra, Petter chose horn balances on the elevators and the rudder, internal balances on the ailerons, and spring tabs on all the control surfaces. The ailerons were particularly clever. The leading edge of each aileron was enclosed in a shroud, a sort of cowling that covered the beak-nose balance. This was a Westland design that Petter had used before, but this time he didn't use a flexible diaphragm to seal the gap. Instead, he simply reduced the clearance between the balanced spine and the spar to less than 1.5 millimeters, about the thickness of a matchstick. To achieve that kind of precision, the shrouds had to be jig-built to exacting tolerances. Get it right and the airflow in that tiny gap would create just the right amount of aerodynamic assistance to make the ailerons light and responsive without being twitchy. The spring tabs were Freddie Page's contribution. He'd used them extensively at Hawker and knew exactly how to make them work. A spring tab is a small surface on the trailing edge of the control that deflects in the opposite direction when you move the stick, using aerodynamic force to help you push the main surface. The harder you pull, the more the tab deflects, and the more it helps. It's like power steering, but purely mechanical. And these spring tabs would play a major role in the Canberra's extraordinary handling. They gave the pilot light, precise control across the entire speed range, from flat out at 570 miles an hour to barely 100 miles an hour on final approach, a great improvement over other aircraft that would either get heavy and sluggish at high speed or twitchy and oversensitive at low speed. The wing carried something rather unusual: 40 hydraulically operated air brake fingers, 20 on top, 20 underneath, that popped up from the wing surfaces like a bed of nails. When deployed, they created tremendous drag without upsetting the wing stability, allowing the Canberra to slow down rapidly or descend steeply without gaining speed. Perfect for a bomber that might need to lose altitude quickly or slow down for landing without floating halfway down the runway. But, like all new aircraft, the Canberra revealed a few teething troubles once it got into regular flying. Pilots occasionally reported what they called freezing ailerons during high altitude climbs in cold weather, a strange condition where the controls would suddenly stiffen up and lateral response almost vanished altogether. The cause turned out to be something deceptively simple. Recall the tiny clearance between the aileron's beak and its shroud? Well, that could bind when the metal contracted in extreme cold. Once identified, the tolerances were adjusted and the problem disappeared. Later, a more serious issue emerged in the early production aircraft: stress corrosion in the high-strength aluminium alloy they had chosen, once thought to be the perfect material for the jet age. It wasn't. Cracks began to appear in spars and forgings, forcing engineers to replace it with a tougher and more stable alloy. It was an expensive lesson in metallurgy, but one that made the Canberras far stronger and longer lived. For the Canberra, it was, in every sense, despite appearances, the right wing for the right aeroplane. But a wing alone doesn't make an aircraft. Petter needed a fuselage to match. Something just as elegant, just as practical, and just as uncompromising in his pursuit of simplicity. In September 1945, Petter was ready to submit a brochure to the Ministry of Supply for what he called the English Electric A1, officially the EA1, the E marking it as an English Electric design. And by December that year, the final configuration had been set. What's important to keep in mind here is that the key requirement was that this aircraft would carry a radar-based bomb aiming system, which meant there would be no human bomb aimer. In fact, the very core of the aircraft's design was around this very idea, which was the very, very advanced radar bombing system, the H-2S Mark IX, that on paper promised remarkable accuracy. It was, without question, the biggest gamble of the entire project, but this wasn't Petter's problem. He was simply told to leave the right amount of space, weight allowance and electrical power load, and wait for the day when a convoy of lorries would arrive, loaded with mysterious black boxes that would supposedly make it all work. Shortly after his submission, the Ministry of Supply issued a contract for the design and manufacture of 4 prototypes of the high-altitude bomber, all with the AJ-65 engine. A bit more on these later on. With this contract in hand, Petter and his team quickly got to work. The fuselage of the Canberra was a masterclass in what Petter called adventurous conventionalism, being bold enough to try something new, but sensible enough not to reinvent the wheel where it wasn't needed. At first glance, it was without a doubt beautifully simple. A long, slender cylinder with a circular cross-section tapering gently at both ends, 6 feet in diameter through the middle, wide enough to be useful, narrow enough to slip cleanly through the air. There was a gentle downward droop ahead of the cockpit to give the pilot a clear view forward, and an equally gentle upward taper at the tail to provide ground clearance during those steep takeoffs and landings, especially important given the short undercarriage that tucked neatly into the wing roots. It looked, in a word, elegant. Many would later call it the most handsome bomber ever built. But the real genius wasn't in how it looked, it was in how it was built. Petter designed the Canberra as 5 independent primary structures, completely separate modules that could be built, tested and even swapped out independently. There was a front fuselage, the center fuselage, the rear fuselage and 2 different wing assembly options depending on the variant. This modular approach was revolutionary at the time. It meant that you could build different variants without redesigning the entire aircraft. Need a photo reconnaissance version? Stretch the fuselage and add a camera bay. Want a trainer? Modify the nose. Need more range? Swap the wing with larger fuel tanks. It was like building with those little plastic bricks, whatever they're called, decades before anyone thought to apply that philosophy to military aircraft design, and it proved invaluable. Over the Canberra's long life, that flexibility allowed it to be adapted and adopted for roles no one had even imagined when Petter first sketched it out. In fact, the Canberra has spawned at last count 40 different versions and variants, with 3 Canberras highly modified B-57s known as the WB-57F still in active service with NASA for high altitude atmospheric research and testing. The fuselage structure itself was semi-monocoque, a fancy term that means the outer skin carries some of the load, supported by an internal framework. Light circular channel frames ran around the circumference, notched to accept longitudinal Z-shaped stiffeners that prevented the thin aluminium skin from buckling under stress. Think of it like the ribs and stringers inside a ship's hull, forming a strong but lightweight cage, with the skin stretched tightly over it. Simple, efficient, and very much of the new jet age. The centre of the fuselage was dominated by the bomb bay, a cavernous space 23 feet long that could carry up to 10,000 pounds of ordnance. The doors were unusual too. Rather than hinging open like traditional bomb bay doors, they slid upwards on 3 roller guide tracks, retracting smoothly into the fuselage. Less drag, cleaner airflow, and no risk of them being torn off in high-speed dives. Above the bomb bay, the roof was a massive grid structure. Longitudinal channel beams are riveted to transverse beams, forming a skeleton strong enough to support 2 large fuel tanks. Forward of that, just behind the cockpit, was a full bulkhead, a solid wall across the fuselage designed to withstand cabin pressure and support the nose wheel, which folded backwards into a well beneath the crew compartment. Moving aft, we come to the tail, another area where Petter's pragmatism and cleverness shone through. The tail was fairly conventional in layout, a standard fin-end rudder with a tailplane and elevators. But there was a twist, literally. The Canberra's tailplane was essentially a scaled-down version of the main wing, mounted on pivot points bolted to a forged frame at the front of the tail section. Why was it pivoted? Well, because the Canberra's tailplane had variable incidence, meaning that it could be tilted electrically to change its angle relative to the fuselage. This meant the aircraft could remain properly balanced during high-speed dives or as its weight distribution changed when bombs were released or fuel was burnt off, keeping the pitch steady, much like a car's cruise control maintains speed. However, this system would prove deadly. A number of early production B-2 models were being lost due to what appeared to be complete loss of control shortly after takeoff, where the aircraft would pitch violently nose up or nose down despite the pilot desperately fighting the controls, only for the aircraft to impact the ground. The losses were severe enough that at one point there were calls to ground the entire fleet until a cause could be found. The investigation eventually traced the problem to a sticky switch in the trimming circuit, which could fail and keep the motor running even after the pilot had released the trim control. This would drive the tailplane to extreme nose up or nose down angles, creating forces the smaller elevator couldn't overcome, leaving the pilot helpless. There was also the suspicion that the original wiring design, which had the power and signal lines bundled together in a single loom along the fuselage, was inducing stray currents in the signal wiring, causing uncommanded trim movements. The system was in effect giving itself orders that the pilot hadn't made. The fix required several simultaneous modifications. A new dipole trim switch was fitted to eliminate the sticking issue, and the wiring was redesigned to separate power and signal looms to stop electrical interference. The actuator's speed was also reduced, its travel limits revised, and the system reconfigured so that the pilot had to actively hold the trim switch before the circuit would energize, ensuring that it was only live when deliberately used. A structural modification known as Mod 2125 further adjusted the elevator spring tab and restricted actuator travel, guaranteeing that even if the system failed full nose down, the pilot retained enough control to recover. These fixes worked, but the problem had already cost lives, and the lesson wasn't fully learned. The same flaw resurfaced years later in the American-built B-57, where the tailplane actuator caused fatal accidents and temporary groundings of the type. It was a sobering reminder that even when problems are solved, knowledge doesn't always travel as far as the aircrafts themselves, and sometimes the same lessons have to be learned twice at terrible cost. On a lighter note, the vertical fin used orthodox spar and rib construction, but with an interesting quirk. The leading edge was made of wood. Why? Because it housed aerials for the radio and navigation system, and wood doesn't interfere with radio signals the way the metal does. Much of the fin was built from plywood, serving as a dielectric housing, essentially a transparent shell as far as radio waves are concerned for the GH navigation aerial. The rudder itself was conventional light alloy, but here's where Petter showed his genius again for practical problem solving. He knew that getting the rudder to balance just right would be tricky. Too much horn balance, that protruding section ahead of the hinge line, and the rudder would be twitchy and unstable. Too little and it would be heavy and sluggish, especially critical if an engine failed on takeoff and the pilot needed full rudder deflection to stay on the runway. But they couldn't test it accurately in a wind tunnel. The tunnels simply weren't large enough to simulate the fundamental aerodynamic forces. So Petter made a brilliant compromise. He built the very top section of the rudder, the horn balance area, out of wood instead of metal. Why? Because if it turned out to be overbalanced, the ground crew could simply cut it down and reshape it between test flights. Interestingly, the RAF even employed a team of carpenters to look after wooden sections of the Canberra. Now, the main gear was particularly clever. And before you ask, yes, I do have to touch everything. Each leg carried a single wheel mounted outboard retracting inward into the deepest section of the wing root, that enormous 19-foot cord giving plenty of room that you can see here in the video. I'm not the tallest, only 5'8" in socks, and I could comfortably stand up in the wheel well. It was very quiet in there. The inward retraction meant the wheels tucked away cleanly without needing bulky fairings or blisters on the underside of the wing. The undercarriage structure used the same strong aluminium alloy as the wing spars, but this would later cause problems. Within a few years of service, stress corrosion cracking started appearing in the undercarriage components, which meant that the RAF had to start instituting regular inspections using ultrasound, cutting-edge technology at the time, to detect cracks before they became dangerous. But here's the thing about all of this. The fuselage, the modular construction, the wooden rudder, the variable incidence tailplane, it all worked together as a system. You see, Petter wasn't just designing parts, he was designing an aircraft that could be built quickly, modified easily, and adapted endlessly, and that flexibility was over her lifetime to be tested in ways nobody had anticipated. By late 1947, the Canberra project was in crisis while a full-scale mock-up was taking shape. At the heart of the project was that H2S Mark 9 radar, an ambitious piece of technology that promised to let the crew see through cloud, rain and darkness and strike their targets from high altitude with pinpoint accuracy. But this sophisticated system was running years behind schedule. Engineers discovered that this radar was far more complicated, far heavier and physically larger than anyone had anticipated, and it would never fit into the A1 airframe. Not only didn't it fit, but the system required bulky transmitters, cooling equipment, and an enormous antenna. It would have taken up nearly all the available space in the aircraft's nose, and then some. This was a disaster. The radar was supposed to be the Canberra's defining feature, but instead it had just become its most significant obstacle. Without it, the bomber's core capability, the ability to strike targets it couldn't see, was impossible. The original specification B3/45 had been crystal clear on this point. The aircraft must allow accurate bombing without visual contact with the target. As you can imagine, a lot of midnight oil was being consumed to get the radar in a state where it could be made to work in the space available. But the engineers inside the telecommunications research establishment who were developing the system had to admit they were years away from delivering something that would actually work and fit inside the aircraft. And so in early 1947, the Ministry of Supply had to accept the reality of the situation. The radar wasn't going to be ready in time. But rather than delay everything and wait for technology that may never arrive, the ministry made a pragmatic decision. The radar-aimed high-altitude bombing mission would be assigned to the V-bombers. Maybe, hopefully, it would be ready by the time they flew. But in the meantime, what to do with the A1? If it wasn't going to be used for the purpose for which it was conceived, then could a new role be found for it? Petter and his team, rather than shrug their shoulders and accept defeat, started to look for alternative concepts for new missions their creation could fulfill. What they proposed was to replace the complex radar bombing system with an updated wartime navigation system paired with a visual bomb sight in the nose. The trouble with that idea was that the crew would need to physically see their target using Eyeball Mark 1. This decision had an immediate ripple effect through the design. To operate the eyeballs, a third crew member, a dedicated bomb aimer, had to be added to the crew count. And this is where the modular design philosophy paid off immediately. Petter's sleek two-seat cockpit was now redesigned for three: the pilot, the navigator and the bomb aimer, who would lie prone in a new perspex glazed nose to visually line up bombing runs, giving him an unobstructed view downward and forward. The new specification was a little more conservative, with a reduced range from the original B3/45 1600-mile range to just 1,000 miles. Nevertheless, the ministry accepted this new range as they drew up a new specification B5/47. Despite the new specification, the 4 A1 prototypes already on order would continue to be built to the original B345 requirements as testbeds, but any further aircraft would be built to the updated B547 standard, which would become the first production Canberras, the B2 variant, that would have the visual bombing kit and the 3-man crew. The Canberra's expected high-altitude performance was not overlooked either. With advances in long-range cameras, the aircraft's potential for reconnaissance was not missed, and as such, the first of the exceptional spy-in-the-sky versions, the PR3, was drawn up. This model would have a crew of 2 and carry numerous large cameras, with part of the bomb bay being converted to a 400-gallon fuel tank, increasing range over 3,000 miles. And finally, a third variant, the T4. This would be a dual-seat trainer, but more on these versions later on, because this was all in the future. And right now, inside English Electric, there was further consternation. If the radar crisis had shaken the program, what emerged next nearly killed it. By November 1947, just as the specification change was being finalised, a new problem surfaced, and this time it wasn't about how the Canberra would find its target, but how she would fly to her target. The Rolls-Royce AJ65 was supposed to be the engine that made everything possible. It was compact, powerful, and a diameter slim enough to fit inside nacelles without ruining the aircraft's clean lines. But there was a problem. Despite earlier assurances, the engine still didn't work. Now, to understand why this was such a crisis, you need to understand what an axial flow engine actually is and why it was so difficult to get it right. In a jet engine, you're essentially trying to compress air, mix it with fuel, burn it, and blast it out the back to create thrust. Simple in concept, brutally complex in execution. There are two main ways to compress that air. The simpler method, if we can call it that, uses a centrifugal compressor. Imagine a spinning disc that flings air outwards like water spinning off a plate, squeezing it against the outer casing. Engines like the Rolls-Royce Nene, Ghost and Derwent used this design. It was reliable, well understood and relatively easy to build, but it was also bulky. The compressor had to be wide to work efficiently, and in turn meant a wider engine, which meant fat engine nacelles that created drag. The more elegant solution was the axial flow compressor. In these engines, instead of flinging air outward, it pushes air straight back through a series of rotating blades and stationary vanes, like a fan forcing air through progressively tighter channels. Each stage compresses the air a little more, building up pressure gradually. Done right, you get a much slimmer engine with better efficiency and more power. Done wrong, and you get a disaster. And in 1947, Rolls-Royce was getting it very wrong indeed. And it was mainly due to something called surging. Think of the engine like blowing air through a set of straws. If everything's smooth, the air goes through perfectly. But if one of those straws gets kinked or blocked, the air pushes back and the whole system shakes. That's what was happening inside the AJ65 during a surge. In an axial compressor, it happens when the airflow through those carefully designed blade passages suddenly separates and stalls, like an aircraft wing losing lift. The smooth compression breaks down into turbulent chaos, pressure spikes, engine splutters and loses thrust. Worst case, it stops altogether. And the AJ65 was doing this constantly on the test bench at Barnoldswick. To quote Stanley Hooker, in 1946 we had the first AJ65 engine on test. It was difficult to start, would not accelerate, broke its first stage blades and could only be coaxed reluctantly to 5,000 pounds thrust. It was, comparatively speaking, a hell of a mess. That admission from one of Britain's top aero engine designers tells you everything. This wasn't a minor snag, it was a fundamental failure. Rolls-Royce threw everything at the problem: variable instance guide vanes that could adjust to different airspeeds, blow valves to dump excess pressure, but the compressor stubbornly refused to behave. And to make matters worse, they were also unhappy with the big single-stage turbine that drove it, which was proving clumsy and inefficient. The failure led to panic at Rolls-Royce, with the entire compressor program being moved from Barnoldswick to Derby, where Lord Hives, the managing director himself, would take personal charge. It was clear that a significant development program was required to match the pressure rises through each stage of the compressor, and that blow-off valves would be needed during starting and acceleration. For Petter, this was an absolute nightmare. He'd designed the entire aircraft around those slim axial engines in nacelles that were perfectly sized and fitted to an aerodynamically clean and optimized wing. Everything depended on those AJ65s fitting exactly where they were supposed to and delivering the power they'd promised. If the AJ65 failed, the alternative was the Rolls-Royce Nene, that reliable old centrifugal engine. But the Nene had a diameter of nearly 50 inches compared to the AJ65's 42. It would mean fat nacelles bulging from the wings, conventional engine installations like the Gloucester Meteor, and all that beautiful aerodynamic cleanliness ruined. It was precisely what Petter had been trying to avoid. There were some at English Electric that suspected that offering the Neens was smooth salesmanship from Derby, Rolls-Royce hedging their bets and offering their proven engine as a fallback. Curiously though, no one offered the Metropolitan Vickers F9 as an alternative, a superb axial engine that was actually working well and was slimmer than the Neen. The F9's design went like a bomb, as one engineer put it. But I suppose in 1947, Metropolitan Vickers was trying to exit the aviation business entirely, and the Hawker-Siddeley Group hadn't yet taken over the design, which would later become the highly successful Armstrong-Siddeley Sapphire. Still, Petter couldn't afford to gamble everything on the AJ65's working. The program was already reeling from the radar fiasco. If the engines failed too, there might not be a Canberra at all. So in the autumn of 1947 he made a pragmatic decision. The second of the 4 prototypes, VN813, would be fitted with the Neen engines as an insurance policy. It would be a bitter compromise if they had to use these power plants, since the Neen produced only 5,000 pounds of thrust per engine compared to the Avon's promised 6,500. The fatter, less elegant nacelles would increase drag significantly and reduce the aircraft's critical Mach number, a serious penalty at high altitude where every fraction of a Mach number mattered. But they had to accept the fact that although it would be slower and less elegant, she would still fly. And if the AJ65 development collapsed entirely, English Electric still would have a Canberra to continue testing the airframe, the systems and handling characteristics. The issue of aesthetics was always important to Petter, but then isn't it important to all of us? He would later give a paper to the Royal Aeronautical Society in which he compared creative aircraft design with great art and poetry. He genuinely believed in a correlation between aesthetics and engineering efficiency. If it didn't look right, it probably wasn't right. And the Neen installation didn't look right. Eventually, Rolls-Royce made the AJ65 engine work reliably enough for service. These engines would go on to become the Avons, the Merlins of their time. They refined the compressor aerodynamics, threw out the clumsy single-stage turbine and replaced it with 2 more lightly loaded stages, and they gradually tamed the beast. 2 prototype Avons were putting out 6,000 pounds of thrust, not quite the promised 6,500 but close enough, when they were installed in a Lancastrian testbed. It would take several more years of development at Rolls-Royce before the Avon RA3 finally delivered that promised 6,500 pounds of thrust and powered the early Canberra B2s and PR3s into service. However, the early production Mark 101 engines retained that nasty habit of surging if not handled correctly. The solution wasn't an elegant engineering fix, but rather a careful procedure for managing the throttles during takeoff. Inside the engine, 2 position inlet guide vanes controlled airflow through the compressor, optimizing performance at different power settings. Under certain conditions, particularly during rapid acceleration from idle as pilots advance the throttles for takeoff, those inlet guide vanes could stall. The internal airflow would break down momentarily and the engine would surge with a bang or a cough, losing power just when they needed it most. Losing thrust during takeoff is terrifying under any circumstances, but the real danger came from asymmetric thrust. If one engine surged while the other was at full power, the aircraft would yaw violently towards the dead engine. The pilot would have to react instantly with aggressive rudder input to maintain directional control, and if the surge happened at a critical moment during the takeoff roll, there might not be enough runway left to stop or enough speed to fly. The problem was particularly acute during crosswind takeoffs, because the disturbed airflow around the engine intakes made the inlet guide vanes stall in more likely. The crews developed a specific, if rather cumbersome drill that added complexity and time to every takeoff in strong crosswinds. The aircraft had to be positioned into the wind on the runway and held on the brakes while the throttles were advanced, waiting for the inlet guide vanes to open and the engines to stabilize at high power. Only then could the aircraft be edged around onto the runway heading before takeoff power was applied fully. It worked, but it required discipline and careful technique, but for now, the ministry was satisfied with the in-flight performance of the Avon. At least its availability was no longer a question mark hanging over the program. And in March 1949, they seemingly had such confidence in the whole affair that they placed a production order for 132 aircraft, a mix of the tactical bomber, photo reconnaissance and trainer. You could almost call this aircraft the TSR-1. This endorsement, this act of faith, was unusual, a decision in no small part influenced by the increasing hostility of the Soviet Union and desperate need for a fast modern aircraft. Bomber Command couldn't just wait around for the V-bombers to appear. But in those dark months of 1947, it had come perilously close to killing the entire program. Between a radar failure and the engine crisis, the Canberra had faced two existential threats in less than a year. Both times, Petter's pragmatism, that willingness to accept compromises he hated in order to keep it moving forward, had saved it. Pity he didn't do the same for the Nat. Anyway. The modular design allowed the radar mission to be abandoned and the nose redesigned. The insurance policy of the Neen installation kept development moving while Rolls-Royce wrestled with the Avon. If it looked right, it probably was right, and the Canberra was starting to look very splendid indeed. By 1948, Petter and the whole design team had moved to the deserted ex-USAF maintenance base at RAF Warton, several miles from Preston. But even with the engines sorted and the radar crisis managed, there remained one critical position to fill, perhaps one of the most important of all. They needed a chief test pilot. Now, that might not sound particularly dramatic. After all, every aircraft manufacturer has test pilots. But this wasn't about finding somebody who could simply fly the aircraft and report back. Petter needed someone who could bridge two worlds, the world of operational flying and the world of experimental design. He needed someone who understood what pilots actually needed in combat, not just what looked great on paper. Someone who could sit in the design office and argue about cockpit layout, control field, visibility and ergonomics before a single rivet was hammered. And someone who could spot a problem early when it could be fixed relatively cheaply rather than after the prototype was built. English Electric had several competent production test pilots at Salisbury factory, experienced men who'd been testing aircraft throughout the war. But none of them had the experience with experimental prototypes, the risky, unpredictable first flights where everything is unknown. And worse, from Petter's perspective, they all reported directly to Arthur Sheffield, the works manager. He simply couldn't tolerate having his chief test pilot going over his head to Sheffield in areas of technical disagreement. The test pilot had to be part of a design team, answerable to Petter and Page, not the production side of the business. So with Freddie Page's agreement, Petter decided to look outside English Electric entirely and make his own appointment. It was a deliberate challenge to the establishment, bringing in an outsider for such a critical role. It wasn't long before Petter had narrowed it down to two candidates. The first was squadron leader Tony Martindale, who'd achieved considerable distinction at the Royal Aircraft Establishment in high-speed diving tests. Martindale had survived some remarkable experiences, including landing safely after the total loss of a propeller from a Spitfire in a vertical dive at Mach 0.9, the kind of hair-raising incident that separates test pilots from ordinary mortals. Crucially, he also had a degree in engineering and could be relied upon to match practice with theory. The second was Wing Commander Roland Prosper Beamont, universally known as B. Beamont's credentials were formidable, but different. Between 1939 and 1946, he'd completed 3 tours of operations with the RAF, flying Typhoons and Tempests in ground attack, defending against V-1 flying bombs, and engaging in air combat over France and Germany from D-Day onwards. As commanding officer of No. 609 Squadron, he'd become famous for train-busting attacks. These were daring low-level attacks against the German transport and supply lines. After the war, he'd spent time on jet fighter development with the Meteor at Gloucesters, then 2 spells as experimental test pilot at Hawker Aircraft. Beamont was therefore well known to Freddie Page, who'd worked at Hawkers for years. Petter, the brilliant pragmatic engineer, initially favoured Martindale. The engineering qualifications were compelling. Martindale could analyse problems, run calculations, understand the theory behind what was happening. That appealed to Petter's methodical mind. But there was a catch. Martindale worked at the RAE, the Royal Aircraft Establishment, and might be expected to express technical opinions that reflected the establishment views rather than Petter's. Petter had already had his share with confrontations with establishment figures during his time at Westland, and he developed strict ideas about limits to which he would allow recommendations from anyone, even his test pilot. But Freddie Page saw it differently. He took the view that there would be an abundance of engineers on the team. What they needed wasn't another theorist. They needed someone with extensive operational experience, someone who'd flown jets in anger, someone who knew what worked and what didn't from a pilot's perspective. Page cast his vote firmly for Beeman. Petter, to his credit, conceded. And in 1947, Roland Beeman joined English Electric Aircraft Division as chief test pilot. Interestingly, this wasn't Beeman's first encounter with Petter. He'd actually been interviewed 6 months earlier, and neither man had been particularly impressed with the other. Beeman was asked to provide a reference and suggested a very senior air marshal. What Beeman didn't know, and wouldn't discover until many years later, was that the air marshal had advised against his suitability for the post. But Page's advocacy won out, and it turned out to be one of the best decisions Petter ever made. Beeman's first task was immediate and critical: determine a cockpit layout. He sat with a design team working through mock-ups of the front fuselage, planning where every instrument, every switch, every control should go. It wasn't glamorous work, but it was vital. Get it wrong and pilots would struggle with the aircraft for decades. His involvement guaranteed that the Canberra's office, the pilot's working environment, would be more functional than what many aircrews received in new types. Everything was positioned with an operational pilot's perspective, not just an engineer's logic. There was one particularly charged confrontation early on. Beeman challenged a decision he thought fell within his area of responsibility. According to Beeman's recollection years later, he said, "Petter seemed to explode, and I said perhaps we'd better forget our arrangement and I would write out my resignation forthwith." "All right," he said, and I was dismissed. About half an hour later, Petter sent for him. "We must not be too hasty," he said. No further confrontations ever occurred. Beeman always stood his ground on all matters relating to safety and operational requirements, but he didn't try to take over the role of the technical staff. He developed high confidence and respect for the engineers, and they for him. Their relationship worked because both sides understood their boundaries, and when it came time to demonstrate what the Canberra could do to show the world what Petter's team had created, Beeman's aggressive but highly skilled approach to flight demonstrations would prove invaluable. His faith in the robustness of the design, his willingness to throw the aircraft around like a fighter rather than a bomber, would go a long way towards persuading potential customers of its virtues. But all of this was still to come. First, the aircraft actually had to fly. By early May 1949, the first prototype A1 was finally ready. The N799 sat gleaming on the Warton tarmac, painted in distinctive cerulean blue that would become synonymous with the aircraft. Apparently, Petter was so taken by the colour that he had the spray shop use the last of the paint to have his car done in the same colour, and it was henceforth known as Petter Blue. You know we'd have done the same. Everything that could be checked on the ground had been checked. The engines had been run, the systems tested, the controls exercised. Now came the moment of truth. This wasn't just another prototype, it was Britain's first jet bomber, the first British aircraft designed specifically around the axial flow engines, the first major design to emerge from this new team at Preston. If it succeeded, RAF Bomber Command's capability would double overnight and Britain would join the big boys jet bomber club. If it failed, well, all of that evaporated, and the critics, and there were plenty of them, doubting whether English Electric had the expertise to pull this off, would be vindicated. The pressure on these men must have been immense. It's safe to say that many at English Electric fully grasped just how much was riding on this single flight. But in typical North Country Lancashire stoicism, there was no drama. Funnily enough, despite how much was riding on this aircraft, there was no ceremony, no brass band, no opportunistic politician craning in for a photograph, just a few engineers and whomever happened to be strolling across the tarmac that morning. The date chosen for this very British event was Friday, May the 13th, 1949. Yes, Friday the 13th. That morning, Petter mentioned to Beeman that they could delay if he wanted. Not everyone considered it to be an auspicious date. Beeman's reply was characteristically direct. Why worry? It's a nice day, and we're serviceable. The weather cooperated beautifully, with light winds from the northwest, clear skies with just a hint of haze, and perfect visibility. You couldn't ask for better conditions. And true to form, Petter then vanished, refusing to hover over his team while they worked. He'd later reappear for the debrief, but during the flight itself, he wanted everyone focused on their jobs without distraction. Shortly after 11:40 in the morning, Beeman climbed into the cockpit and ran through the pre-flight routine. The Avians lit smoothly, their distinctive whine building to a steady hum, and everything looked good. A Vampire chase plane circled overhead, ready to observe and report anything the pilot couldn't see from inside. The tower cleared VN 799 for departure, and Beeman released the brakes. The acceleration wasn't dramatic. With a full fuel load, the aircraft was heavier than during the earlier taxi tests, and at 65 knots, the nose wheel lifted, and at 80 knots, with a gentle pull on the column, VN 799 was airborne, climbing away from Warton for the first time. Beeman kept the speed moderate, established a shallow climb, and began his checks. Undercarriage retraction was smooth with 3 green lights, the engines were running perfectly and the flight controls felt responsive and precise. Then he tried the rudder, and immediately something felt odd. A small input to the right made the nose yaw left as expected, but then the yaw suddenly increased with a jerk and the pedal force seemed to drop away sharply. When he centered the rudder, the nose snapped back, but the movement felt lumpy, non-linear and distinctly wrong. This needed investigation, but not down low where a problem could become critical quickly, so Beeman continued to climb to 10,000 feet, leveled off and throttled back to a comfortable cruise. That's when he realized something quite remarkable. The aircraft was extraordinarily smooth and almost eerily quiet. There was no wind noise around the canopy, no vibration through the airframe, nothing rattling or buzzing. When he released the controls, the Canberra simply continued flying. Perfectly trimmed and perfectly balanced, small inputs on the elevator and ailerons produced immediate, precise responses. The aircraft felt alive under his hands, communicating clearly and responding exactly as intended. It felt like a thoroughbred. Okay, that's enough for waxing lyrical. It's safe to say that Petter and his team had cobbled together a fine old kite. But that rudder issue was still there, and with the Vampire close alongside to observe, Beeman deliberately provoked it again with the same result, a sudden lurching yaw and lumpy pedal forces. He called across to the pilot in the Vampire. "Did you see that wiggle?" The reply came back, "No, but it looks damn nice from out here." Everything else was working perfectly, and Beeman was tempted to continue with the planned test program, exploring low-speed handling and really wringing out the aircraft's capabilities. But those engines were brand new and largely untested in flight, and if one failed on him, he would need aggressive rudder inputs to maintain control, and that anomaly could turn a manageable situation into a catastrophe. Better to land, fix the problem, and fly again tomorrow. The touchdown was gentle at 85 knots, the nose wheel settled in smoothly, and the aircraft rolled out and stopped in about 800 yards. 30 minutes from takeoff to landing. Not a long flight, but long enough to know they had something special. Back at the hangar, the ground crew's reaction was typically understated with the Northern Reserve in full effect. So there were no problems then. Well, why would there be? As if they just witnessed something routine rather than historic. In Petter's office, the atmosphere was obviously relieved as Beeman delivered his report methodically. Everything worked perfectly except the rudder, which felt overbalanced beyond small deflections. They'd investigate and fix it before the next flight, and here's where that wooden rudder horn proved its genius. By the end of the day, the decision was made to trim the horn balance progressively until they got it right, Because it was wood, they could modify it quickly between flights. 5 days later, on May the 18th, Beament flew VN 799 again with a reduced horn balance, and the rudder felt perfect. He pushed the envelope further to 420 knots and 15,000 feet, and control and stability were excellent. But a new problem emerged. Above 400 knots, a vibration started. 6 to 10 cycles per second felt through the whole airframe. It was heavy, thumping, and worrying because it felt like flutter. Flutter is one of the most dangerous phenomena in aviation. It's a self-reinforcing oscillation where aerodynamic forces and structural flexibility couple together, building amplitude until something breaks. And if you don't catch it early, it destroys the aircraft. Over subsequent flights, they explored the limits cautiously, and at Mach 0.77, the aircraft developed a slight snaking, a gentle oscillation in yaw. By late May, with sensors fitted, they traced the vibration to early signs of elevator flutter, a dangerous resonance building up in the tail. On May the 31st, Beament took Di Ellis up to experience it firsthand. At 10,000 feet, he deliberately flew into the flutter boundary and held it there with the airframe shaking violently and the instruments blurring. "What do you think of that, Di?" Beament asked after throttling back to smooth air. "Christ," came the emphatic reply from Di Ellis. "Well," said Beament, "we'll just go and have another look." But Di wasn't having any of it. He'd seen enough. "I think we should investigate this on the ground." So VN 799 was grounded for a month while modifications were made to the elevator mass balances and horn shapes. The wooden rudder was finalized into its production configuration, and engineers traced that snaking to the turbulent wake behind the canopy. This was easily cured with a simple fairing that smoothed the airflow onto the fin. When testing resumed in July, progress was rapid, with flight after flight expanding the envelope methodically. On August 11th, they exceeded 40,000 feet for the first time, reaching 42,000, and the next day they hit Mach 0.8. By the end of August, they'd achieved 470 knots indicated airspeed, comfortably exceeding the proposed service limits. Throughout all of this, one thing became increasingly clear. The Canberra's handling was exceptional. That low wing loading and high thrust to weight ratio gave it an agility that seemed impossible for a bomber. Even at 40,000 feet, it could maneuver like something far smaller, which gave Beament an idea. The Farnborough Air Show was scheduled for early September, and traditionally, bombers were displayed flying sedately past the crowd in straight lines, demonstrating speed but little else. Beament thought the Canberra deserved better. He'd put his ideas to the team. There was some pushback suggesting they shouldn't risk the prototype with aggressive flying because bombers weren't really meant to be aerobated. But Petter's response was simple. His chief test pilot would know best how to present the aircraft, telling Beament, "Do what you think is right." So on August the 22nd, returning from high altitude testing, Beament tried some maneuvers. Full rolls, rolls off loops, complete loops, fruit loops, all the loops. Everything was smooth and controllable, though speeds above 350 knots required some serious muscle on the unpowered controls. After all, this was still a bomber, not a nimble fighter. Over the following week, he refined a 6-minute routine that would showcase everything that Canberra could do. On September the 4th, VN 799 flew to Farnborough, with its blue finish polished to a gleaming shine and the name Canberra freshly painted on the nose. Opening day, September the 6th, started with an embarrassing glitch. To keep the centre of gravity within limits with the lower thrust prototype engines, they'd planned to fly with light fuel loads, burning off the rear tank during taxi and only using the forward tanks for the display. But no one had properly checked how low you could run those tanks before losing fuel pressure. So, with the crowd watching, VN 799 taxied out, lined up for takeoff, and the port engine died from fuel starvation. Grey smoke poured from the tailpipe as unburnt fuel hit the hot exhaust. Petter, watching from the crowd, was horrified. He vaulted the barrier and sprinted across the active runway to his stricken aircraft, demanding that the tanks be filled completely. Beeman explained it was simply a tank selection error, easily corrected, and Joe Sargison, the engineer in charge, made the brave decision to ignore Petter's order and stick with the planned fuel load. The display was rescheduled for the end of the day, and Petter later wrote to Sargison, "You kept your head when others failed. Take 3 days leave." Finally, as the last item of the day, VN77 rolled for takeoff, and what followed was 6 minutes of glorious flying that made aviation history. The Canberra practically leapt into the air in barely 700 yards, with Beeman pulling it into a steep climbing turn, reversing direction in a dramatic dumbbell pattern over the crowd. A low, fast pass at full power followed, then a vertical pull-up in front of the tower, rolling inverted at the top into a half loop before diving back down toward the boundary and snapping into a 360-degree roll along the length of the runway. He pulled it into a vertical bank around the perimeter at 4G in front of the spectators, then executed a wing over while lowering the gear, followed by a slow pass with the wings rocking violently to show full control near stalling speed. Gear up, throttles forward, another dumbbell turn, and then the finale, a half loop rolling out inverted with gear and bomb bay doors extending, spiraling down in a tight descent to land. As the bomb bay doors opened during the final spiral, something came loose. The test instrumentation pack in the bomb bay tore free, trailing wires from the fuselage and causing some instruments to fail. But both engines kept running and Beeman brought it down smoothly, the end to a spectacular display. Can you imagine the looks on the faces of the crowd? They must have been stunned because nobody had ever seen a bomber fly like this. It looked like something far smaller, far more agile, and the straight wing that had seemed old-fashioned on the ground had just demonstrated capabilities that seemed impossible. But not everyone saw it the same way. The next morning, Beeman was summoned before the display committee and told, "Tone down your display." But when he asked if it had been dangerous, the response was, "Well, no, but just cool it." It turned out that one of the committee members responsible for aviation insurance had protested that he had never seen anything like it and wasn't prepared to cover it. However, Mutt Summers, Vickers' chief test pilot and senior pilot on the committee, defended Beeman after confirming the aircraft was being flown well within its tested limits, so the routine could continue unchanged. For the rest of the week, VN799 repeated the display daily, each performance as dramatic as the first, and Robert Holtz, editor of America's Aviation Week magazine, captured the impact perfectly. The biggest military surprise of the show was the English Electric Company's Sky Blue Canberra bomber. US observers were not impressed with the Canberra straight wing, a somewhat conventional configuration on the ground, but in the air, the combination of test pilot R.P. Beeman and the thrust from the two axial Avons made the Canberra behave in a spectacular fashion. The world had never seen anything like it, and everyone wanted one. In fact, it was Australia's early interest in the aircraft that inspired its name, chosen in the hope it would encourage them to place an order. But it wasn't until January the 19th, 1951, during a formal christening ceremony, Australian Prime Minister Robert Menzies officially named the aircraft Canberra. If you recall, the initial contract had called for 4 prototypes, and by the end of the year, all of them would be flying. It's important to point out that the 4 A1s were retrospectively designated as the Canberra B Mark I, built to the original B345 specification, all with the solid noses and the original crew count of 2. The second prototype, VN813, finally took to the air on November the 9th, 1949, with Beeman again at the controls. This was the insurance policy, the aircraft fitted with those bulbous Neen engines that Petter had so reluctantly accepted as a backup when the Avon development had looked like it might fail. Looking at the photos, it's hard to see much of a difference between the 50-inch diameter of the Neen and the Avon's 42 inches, but Beeman noticed the performance penalty of the fatter engine nacelles immediately. The bulkier nacelles seemed to reduce the limited Mach number by 0.05 or just over 30 miles an hour compared to the Avon powered first prototype, a significant handicap at high altitude where every fraction of a Mach number mattered. Still, the N813 served its purpose. The insurance policy had worked, and now that the Avon had proven itself, the Nene-powered aircraft became a useful testbed for systems and handling characteristics without tying up the higher performance Avon variants. It would later be retained at Warton and used by Rolls-Royce for various development programs, including eventually serving as a flying testbed for the de Havilland Spectre rocket motor, a perfectly useful aircraft but never the star of the show. Just 13 days after VN813's first flight, the third prototype, VN828, flew from Samlesbury on November the 22nd with Beaumont once again in the cockpit. This aircraft was built to the same B1 standard as VN799, powered by those now reliable Avon RA2 engines and finished in Bomber Command colours. It was the first of the prototypes to delete the dorsal fin fillet, a small but significant refinement. VN828 would make its own contribution to the programme's growing reputation when on January 16, 1950, it became the first Canberra to reach 50,000 feet, proving that the aircraft's high-altitude capability wasn't just theoretical but genuinely achievable in operational conditions. That achievement mattered because it showed that the Canberra could operate in airspace where most fighters of the era simply couldn't follow, giving it the sanctuary of altitude that defensive armament would have provided to more conventional bombers. In 1955, VN828 was sent to Bolton Pool as a trials aircraft to test new canopies, radar, gun packs, new nose to the BI-8 version, and some other upgrades to the crew compartment. The fourth and final prototype, VN850, flew from Samlesbury on the 20th of December 1949, piloted this time by J.W.C. Squire, who would go on to become Chief Production Test Pilot and fly more than 3,000 Canberra test flights over the following years. VN850 was the last of the original four B1 standard prototypes to retain the dorsal fin fillet, and it was the first to incorporate fuel lines for carrying wingtip fuel tanks, another refinement that would prove valuable for extended range on reconnaissance variants. She was also the first to be displayed overseas when she made an appearance at the Paris Air Show, along with showing up at the 1950 Farnborough Air Show that you can see here in the video. But tragically, both VN850 and her pilot were lost on June 13, 1951. During an engine trial flight, Rolls-Royce test pilot R.B. Leach suffered an engine fire that brought the aircraft down as he attempted to land. However, in those final weeks of 1949, with all four prototypes now flying and the flight test program progressing rapidly, the mood at Warton and Samlesbury was optimistic. And why not? The basic design had no significant faults, the handling was exceptional, and the performance exceeded expectations. At this point, what could possibly go wrong? Beneath the Triumph at Farnborough, cracks were forming in the foundation of English Electric's aviation program, and it's here where I'll say that there was most definitely trouble at mill. And by late 1949, those cracks had become a chasm that threatened everything they'd built. The problem wasn't technical. The Canberra was, as mentioned before, exceeding expectations, production was ramping up, and the P1 supersonic program, which would later become the Lightning, was gaining momentum. The problem was organisational, political and deeply personal, and it centred on one man, Teddy Petter. From the very beginning, there had been tension between Petter's design team at Warton and the established engineering works at Strand Road in Preston. These weren't minor professional disagreements or occasional clashes of personality, and by 1949 they had deteriorated into what could only be described as interdepartmental warfare, with both sides dug in and unwilling to compromise. Arthur Sheffield, English Electric's general manager, made his feelings abundantly clear. "What that carnival lot at Warton want," he was widely quoted as saying, "is English Electric Aviation in 10-foot letters over the main gate at Warton. They'll never bloody get it." From Sheffield's perspective, the Warton team were newcomers who didn't understand the realities of production engineering. They designed things without considering how they'd actually be built, made demands without understanding the constraints, and seemed to think they were somehow separate and superior to the rest of English Electric. It was infuriating, and Sheffield wasn't shy about expressing it. But Petter saw it completely differently. To him, the Strand Road works were production-orientated engineers who simply didn't comprehend the designer's philosophy. They wanted to compromise elegant solutions for the sake of manufacturing convenience. They questioned design decisions that had been carefully reasoned, and they constantly interfered with the team's work. The endless infighting was exhausting and counterproductive, and Petter believed there was only one solution: complete autonomy. He wanted Warton established as an entirely separate administration under his control with no managerial links to Preston whatsoever. He wanted his own experimental engineering department, free from Strand Road's interference. He wanted the freedom to run his design organisation the way he believed it should be run, without constantly having to justify his decisions to people he felt didn't understand what he was trying to achieve. There was fault on both sides. Sheffield and his team at Strand Road had legitimate concerns how designs would translate into production, about costs and practicality. But they expressed those concerns in ways that felt like attacks on the design team's competence. Petter and his team had brilliant ideas and uncompromising standards, but they sometimes seemed oblivious to the realities of actually manufacturing thousands of aircraft in a factory environment. Neither side was willing to see the other's perspective, and neither side was willing to bend. By early 1950, with the demanding P-1 supersonic interceptor program building on top of the wave of Canberra success, Petter brought the issue to a head. He made his continued service with the company conditional on getting what he wanted: a separate administration for Warton and an experimental shop there, both under his control. It was an ultimatum, pure and simple: give me autonomy or I leave. Sir George Nelson, English Electric's chairman, regarded this as a potential disaster. Petter was, by this point, recognised as one of the top aircraft designers in the country. He'd delivered the Canberra, he'd laid the groundwork for the Lightning, and he'd built a design team that was the envy of the industry. Losing him would be catastrophic, not just for the company's reputation, but potentially for the programs themselves. Sir Nelson tried desperately to find a compromise, something that would satisfy both Petter and Sheffield, something that would keep the peace and keep everyone working together, but he simply couldn't find one. The attitudes on both sides were too rigid and the positions too entrenched, and ultimately Sir Nelson made his decision. He refused Petter his experimental department, unwilling or unable to override Sheffield and the established Preston organisation. For Petter, that was the end. From December 1949, he had virtually divorced himself from Warton's activities, stepping back from day-to-day involvement even as the program he'd created continued to accelerate. Freddie Page, who'd been his deputy since joining in March 1945, took over the daily management while the situation festered. And in March 1950, Petter formally resigned. It was a traumatic upheaval at the point of major success. Whatever you thought of Petter personally, and he was a strange and strong personality with plenty of detractors, he'd created a powerful team spirit at Warton that was closely dependent on its leader. His vision had driven everything. His uncompromising standards had shaped the culture. His belief in what they could achieve had carried him through the darkest moments of the radar crisis and the engine problems. And now he was gone. Petter immediately accepted a position as Managing Director and Chief Engineer at Folland Aircraft Limited in Hamble, Hampshire, where he would pursue his lightweight fighter concept, work that would eventually produce the lovely little Folland Gnat. Link to my video on the Gnat in the description. But before leaving, he made it known to members of the Warton team who wished to join him that they would be most welcome. But the potential instability that this would create had disturbed the Ministry of Supply so much that Sir George Nelson visited Warton personally to try to persuade key members of the monthly staff, the salaried professionals, to sign fixed-term contracts, something none of them had been offered before. Some signed, some didn't. A few left to join Petter at Hamble. But most stayed, uncertain what the future held, but committed to the programs they'd started. Freddie Page was elevated to chief engineer, and the weight of expectations settled on his shoulders. He was a strong character in his own right, respected by the team, but he wasn't Petter. What he had instead was solid engineering judgment, management skill, and the determination to see the programs through. The Canberra's development would continue, the Lightning program would move forward, and Warton would survive. But it didn't come easily. The initial strains of restabilizing the situation while maintaining firm control of both the Canberra and the new P1 Lightning supersonic programs took their toll on Page, and he suffered a period of ill health. During his illness, the quality of the Warton team was demonstrated to the full as senior specialists like Ray Creasy, Di Ellis, Don Crow, and many others rose to the occasion and kept these vital activities on schedule until Page recovered. It was a time of great uncertainty, and there were many who expressed doubts about Warton's future. But few, if any, of those doubters were members of the team itself. They'd built something remarkable together, and they weren't going to let it just fall apart because the man who'd started it all had walked away. Page would go on to guide the Canberra through its long and varied career for most of the next 20 years, eventually becoming chairman and chief executive of British Aerospace Aircraft Group, the technical head of the entire aircraft industry, and still in overall charge of affairs at Warton, which by then had become by far the largest and most successful aircraft design and production centre in the country. But in those uncertain months of early 1950, none of that was guaranteed. They just had to keep on working, keep building, and keep believing that what they'd created was strong enough to survive the loss of the man who'd made it possible. The Canberra, after all, had been designed to be adaptable, to survive whatever came its way. And now the team who had built it would have to prove that they were just as resilient. And so that's where we'll pause the story. All very exciting stuff. In the next episode, we'll get into the nuts and bolts of the aircraft that followed, the B2, the PR3, the T4, and the others. Plus, the missions that turned the Canberra from a design success into a Cold War icon. We're talking Operation Musketeer, the nuclear test flights, the world records, all the stories that were too big to squeeze into a footnote. You know, that's really what this channel's really become about. I want you, when you stand in front of an old aircraft in a museum or some aircraft forgotten in some field, I want you to see more than just aluminium and paint. I want you to see the late nights, the arguments, the breakthroughs, the people who poured their lives into making it fly. Because these machines aren't just relics. Every single one of them has a story. And this is what at least I hope I'm here to tell. So if you've enjoyed this Canberra episode, please give it a like. And as the youth say, drop a comment. Maybe even hit the subscribe button so you can stay tuned for the next Canberra installment, which is sitting right here on my desk. Well, actually, it's not here on my desk. I don't have a typewriter. It's on my computer. So it'll be the next episode. So until then, thank you very much once again for watching, and I'll see you in the next video. Toodaloo.